In this video, we are going to look at birthday attack. Look at the birthday attack on cryptographic hash functions. Okay, so first, let's look at the basics. This is called birthday attack for the following reason. So in a group of 23 people, and we want to know whether these 23 people, whether there are at least 2 people in this group of 23 people have the same birthday, which means that they have the same day in the same months, okay, but not in the same year, just the same day, the same months. So we can show that for 23 people, there are at least 2 persons with the same day, whose birthday are on the same day and in the same month, has probability greater than 1/2. Okay, so that means it is it's likely. Okay, so it is. So the calculation is this. So we have 23 people. So we can just line them up, right? So let's say this is the first person, second, third, and then we got 23. So the first person could pick any day, could be any day in the same month. So within the so regardless the year, right? So that is so any day. So the second person, since one has already chosen, since one has already been given a birthday, so the second person's birthday cannot be the same as the first person. So that is hence the probability that the second person's birthday differs from the first person, from that of the first person, is 364 over 365, because this person cannot pick the same days. Likewise, the third person, okay, is 363 over 365, and the last person is 343 over 365, because the last person cannot be the same as any one of these already picked. So this is the probability that none of the 23 people have the same birthday, so which is less than 0.493. Hence, at least 2 of them have the same birthday. Is 1 minus this number, so that is greater than 1/2. Okay, so now let's look at the strengths of cryptographic hash. So we're going to look at strong collision resistance, complexity upper bound. So that would indicate the strengths. Okay, so let H be a cryptographic hash function with output length small l, then H will only have at most n, which is equal to 2 to the lth power different outputs. So then the question is 2 to the lth power the complexity upper bound of breaking strong collision resistance? Because you can simply try this many different strengths. Then, of course, there will be 2 of them after you have. So let me bring up the. Okay, so we know that the So by pigeonhole principle, if you have try 2 to the L plus 1 different strings, then there must be if you try 2 to the L plus 1 different strings, then there must be at least 2 strings, X and Y. They are not the same, but they have the same hash value. Okay, so this is by pigeonhole principle. So then we want to know whether 2 to the L is the upper bound, complexity upper bound for brute force attack. So this is a brute force attack. Okay, it turns out the answer is no. The complexity upper bound is really just square root of 2 to the L. And we're going to prove this by birthday attack. So first, let's look at this birthday paradox. From a basket of n balls of different colors, you pick k balls uniformly and independently at random and record their colors. Okay, if the number k is approximately the square root of n, right? So it's just in that range. Then with probability at least 1/2, there is at least one ball that is picked more than once. Okay. And remember the complexity upper bound of SHA-1. So the output length is 160. So this is 2 to the 80. So we mentioned in one of the previous videos. And then for SHA-512, the complexity upper bound is 2 to the 256 instead of 2 to the 512. All right, so let's move this. We can go now to the next slide. Next, we're going to look at the set intersection attack. Okay, so suppose we are given a set of n numbers, okay, and they're just from 1 to n, and then we are going to select uniformly and independently at random k integers from the first set. So we get, let's say, n1 up to nk. We select k integers, and then the second set, we do the same. Select k integers. Then we want to know the probability that S1 and S2 is not empty. So in other words, there will be at least one element, there is at least one integer that appears in S1 and also appear in S2. Okay, so we want to find this probability. That's Q and K. Okay, so we want to find that probability. So, and so we know that for N1 is equal to M1, the probability is 1 over N. So this is uniform at random. So they are not equal, then the probability is 1 minus 1 over n. So fix n1, you let m1 to go for k of them. So they are not equal, then it's 1 minus 1 over n. Now you let n1 to go for k of them, so that will be that. So that's the probability that these two sets destroy. So none of them equal is this. So this is just this. And we know that 1 minus 1 over n. So this is less than e. So in other words, we have this 1 plus x less than ex. Okay, so that's how we get to this. Then hence the probability that these two sets intersects, okay, the intersection of them are not empty. Intersection of these two sets is not empty, is 1 minus this, hence is greater than that one. Okay, so you do a little calculation, then you will know if k is between this range, so that's approximately square root of n, then the probability here that these two sets intersect is greater than 1/2. Okay, let me remove this. All right. Okay, now let's look at a set using set intersection to launch a attack on a document. Okay, so assume that Malice. So this is may first use a legitimate document D to obtain the authority A user signature. So I present a document, and I would like to get you signed. Suppose by protocol, if you present a legitimate document, then the authority would need to sign it. Okay, so that's by assumption. And then Malice produces a new document F that has different meanings from D. Okay, but we're going to show that they will have the same hash value. Okay, so this is for a document. Then Malice can use this C, can use C as a signature for F. Okay, so that's, now we are going to see how this can be done here. Okay, for D, how we can find F using set intersection attack. And remove this. Okay. All right, so how to find document F. So this is how Malice would do. So she prepares a set S1 of 2 to the L over 2 many different documents. Okay, so lots of documents. Okay, all having the same meaning as D. Okay, now remember this small l is the length of output of this hash function. So prepares a lot of documents. Such documents can be obtained by replacing a word or a phrase in D, or rephrasing sentences in D, or using different punctuation, or reorganizing the structure of D. Okay, there are many different ways to do it. But again, this is just a theoretical example. It's doable, but If L is big, then there will still be difficulty. But just assume that we have all kinds of ways to do this. Like a changing passive tense to active, that kind of thing. So then Malice prepares a set of S2, which also has 2 to the L over 2 different documents, but this time they have the same meanings of F, okay, using the same tricks. Now, she computes, okay, H of S1 and H of S2. So it's just compute a hash code for the first set and also for the second set. Now, by the birthday attack, by the set intersection attack, we know the probability that these two sets intersect is greater than 1/2. Okay, so that's what we have. So, and then for the element belongs to both sets, then that will be, so let's say this is D prime, the other one is F prime. So now, Malice will present D prime to the authority, get the authority signatures, and then replace D prime with F prime, so using that same signature. Okay. All right. So this is a birthday attack. So the birthday attack gives us the following. So this is the message we can take home too. So for any hash, if the value, let's say H, if the length H is L, then the strength of this hash is approximately 2 to the L over 2 rather than 2 to the L's power. Okay, so that is birthday attack tells us.